The radioactive isotope carbon-14 emits a beta particle as a decay. The decay of carbon-14 produces an isotope of a nitrogen. State the nature of the beta particle and state where it is produced. What is the nature of the beta particle? Positive, negative? They are produced in all these radiations are produced from the nucleus. For typing instead of typing the answer, I will show the exact answers from marking scheme. So beta particles are electron and from where they're originated or given out, they're originated from nucleus. If you write electron, that actually completed the whole meaning, that because electrons are negative, so they are also negative. Complete the nuclide notation equation for radioactive decay of carbon-14. So it's a beta, so this will be 0 and -1. What will be the superscript here above nitrogen? Means the number. Superscript. When there's a beta decay, even you can work out without just memorizing the equation. You know the symbol for beta. So if total on the top, the superscript is 14, on the right also the superscript should be 14. So for beta, it is written 0. So for nitrogen, it should be 14 so that the sum will not change. What about the subscript for nitrogen? That will be 7 because 7 minus 1 will make 6. The half-life of a carbon-14 is 5,700 years. What is meant by the term half-life? What is the meaning of term half-life? So the definition of half-life I will show from marking scheme so that you can go through. So time for activity, count, number of nuclei or number of atoms to become half. You not only time to decay, you should mention a term half because that's why it is called a half-life. So time taken by radioactive sample to become half of its original value or half of the nucleus to decay or radiation become half or activity become half, we call half-life. So better memorize these definitions so that it. Yeah, that's also right, that every time taken by half of the radioactive sample to become stable. Now, a workman operates a machine that uses a beta particle to determine the level of the liquid in a plastic water bottle that is being filled. So how they're determining the level of the, like, say this is a plastic bottle which is filled with water. So they place a radioactive source collimate the source. Collimate means radiation will come in out in all the direction, but only allow radiation in one way to flow or pass. And the other side, a detector is placed. So how we can determine the level of the liquid? Because what will happen if the liquid level is below, then maximum amount of beta particle will be able to pass. If liquid level is above, then the amount of beta radiation which will pass will decrease. It will change, not to 0, but it will change. The question is, suggests why alpha particles are not suitable for the same purpose. Why we are using beta? Why not alpha? So alpha particle will be blocked, or alpha particle, because if you use alpha particles are not able to even pass through the paper. How they are able to pass through this bottle and then the liquid? So even there is liquid or even there is no liquid, the alpha particle will not give any counts, or there will be no counts due to alpha. Why gamma is not suitable?
Can react with water, I think so.
No, in terms of physics you have to explain. There is ionization caused by the gamma, but you don't have to go on that point. Basically what happened, even gamma having the highest range or greater penetration power, so it can even there is a liquid or there is no liquid, the gamma is able to penetrate or pass through. So the reading on the detector will not change. So if you are using an alpha, there will be no reading on the detector due to alpha. And if you are using a gamma, so with liquid or without liquid, there will be no change in count because gamma is able to pass through the materials easily. So beta is a suitable source here. So alpha would be stopped absorbed by the plastic bottle, and gamma would be absorbed by the liquid bottle, will not be absorbed by the liquid or the bottle, so the reading will not change. Is it clear? Any doubt in these two, C1 and 2? Okay, in this question, and for atomic physics, you don't have to memorize the symbol for the element, even their proton number or neutron number, you don't have to memorize. If any question is there, writing a correct symbol, so they will provide you a table or the symbol directly. Figure 11.1 shows the data about the 9 elements from helium till neon. A carbon-14 is a radioactive isotope with a nucleon number of 14 and a decay by beta. Use the data, any data you need from figure 11.1 to write down the nuclide notation for this decay. So carbon-14 is there. I will use on the right hand side, I will, or left hand side, I will answer. So you have carbon-14. So nucleon number is 14. What will be the atomic number of carbon? What number should be here at the bottom? Which number? So atomic number is 6, so 6 will be there. Then it is emitting a beta particle. So beta is 0 and -1. So the element which is formed, the nucleon number will be 14 and this will be 7. So what should be the symbol of that nuclide? What is the symbol? The element, so that will be nitrogen. We'll put N. So you can see this question, it's a very simple question, and the weightage, it's of 4 marks. The distribution of the marks I will show. One mark is for completing carbon. One mark is for writing 14 and 7. Nitrogen is there, and for beta or electron, write 0 and -1. Okay, in the next question, a radioactive sample is placed close to a detector. The radioactive isotope in the sample has a long half-life. When we say long half-life, so we can say the amount of radiation which are coming out from the source is not changing, or more or less is constant. Like example, if I say half-life is 4,000, 5,700 years, so means it will take lot of time to decay. So it's radiation coming out for the experimental purpose that can be considered as constant. So a detector record 597 count. So we have a detector and a source is placed in front of this detector. Normally we collimate the source. Collimate means we place a thin sheet of lead so that radiation can pass only in one way. So the counts which are recorded by the detector are 597. When we place figure 11.2 show the reading when the different materials are placed between the radioactive sample. When we place a paper, the count becomes 602, means it increases. When we place aluminum, the counts become 598. When we place a thin lead, like completely lead without anything in any gap, we place a sheet of lead thin, the count decreases to 510. Explain whether any alpha, beta, or gamma are emitted from the radioactive source. Any alpha is there, yes or no?
Yes.
And how you conclude there is alpha?
No, there are no alphas because sheet of paper doesn't block him.
Yeah, so basically, sheet of the paper does not or is not changing the. Otherwise, if there was alpha, then the count should reduce or decrease considerable. But there is no considerable decrease in the counts or radiation. It means there is no alpha. What about beta?
Not many.
No beta even, because 597, when you place aluminum it is 598. So basically the counts increases rather than decrease. So when you place a thin aluminum it should decrease. It does not decrease, remain same, so there is no beta. And what about gamma? When you place a thin lead, so yes, there is gamma because the count reduced. So why there was no alpha? Because the count with the paper increases. Why there was no beta? Because counts with aluminum also increases, does not change. And gamma because the count rate reduce when lead is placed. So there is no alpha, there is no beta. Actually, this is a gamma source. Like majority of the radiation which are coming out are gamma radiations. The second variant of May June 2016, that is a similar a composition of a radon 220. is a radioactive, a nuclide notation is there. Describe the composition of a neutral atom. Neutral atom, so the whole atom means neutron, proton, and electron. How many protons will be there? 86. Because it's a neutral atom, so 86 electron. How many neutrons will be there? 220 minus 86. What's the answer? 134. A nucleus of a radon 220 decay to an isotope of polonium by emitting out alpha particle. Complete the nuclide equation for a decay of radon. So this will be 4 and 2. What will be there? The superscript for polonium? 216. And what is the subscript for polonium? That is 84. Then the detector of radiation is placed near a sample of a radon that gives a reading of 720. Half-life of a radon is 55 seconds. Calculate the reading after 720 seconds, ignore the background. So basically, when detector is recording these 720 radiation, we'll consider these all radiation are from source. There is no background. Practically, there are background, but here for question, we don't have to consider background. So it is 720 after 55 seconds. How much? 360. After another 55 seconds. How much? 180. After another 55 seconds. 90. And after another 55 seconds. So it will be 45. So we'll get 45 counts, or counts per second is a unit for the radiation. So it will be counts per second. Because this total interval will be 220 seconds. Then third variant of May-June 2016. A sample contain atoms of particular isotope, protactinium. The nucleus of this protactinium isotope contain 91 protons and 143 neutron. What will be the value of X, the atomic mass, the sum of neutron and proton? 234. And what will be Y? That's equal to 91. The isotope is radioactive and it decay by emission of beta particle to an isotope of uranium. Complete the equation. So for protactinium, this was 234 and 91. What will be the superscript? So that will be 234. And what is the subscript? That is 92. The radiation detector measure the background counts of background radiation in the lab, and these background radiation are 32 counts per minute. Don't bother about this number because this is a unit for radiation detector. Don't bother about this. It can be counts per minute, counts per second, counts per hour. You don't have to bother about this unit. Just the important thing is the number. So 32 radiations are there from the background. Stay suggest to naturally occurring sources of the background radiation. Naturally occurring sources like things which are giving background radiation naturally. So you can mention rocks, buildings, earth, ground, air. You can mention which is having a radon or cosmic radiation or radiation from galaxies, sun, stars. These are the sources of background radiation. The sample is placed in the lab close to radiation detector. Nuclear station is not the natural. In the question, if you see, they mention naturally occurring. So power station, nuclear power station, we are building. That's why it is not naturally there. It is artificial, like man-made. The sample is placed in the lab close to a radiation detector. The counts are 544. The isotope of protactinium has a half-life of 400 minutes. Predict the value of the count rate measure 1200 minutes. But you have to keep in mind, because this is a continuation of the question, what are the background radiation? 32 are the background radiations. The radiation detector measured 32. So 32 are the background radiation, and total reading on the detector is 544. So the detector reading is equals to source plus background. The detector reading is 544. Background radiations, as you can see, 32. So how many radiations are there from the source? How many radiations are there due to the source? That is 512. So only the source radiation will become half. So after because it is half-life 400 years and we want after 1200 years. Sorry, by mistake. It is 400 minutes and we have to find after 1200 minutes. So basically the source radiation, if it is 512, it will become half after 400 minutes, 256. After further 400 minutes, 256 divided by 2, 128. After further 400 minutes, 64. So basically, after total time interval of 1200 minutes, you will get 64 radiation from the source, but the detector is recording both radiation, source and surrounding. So what will be the reading on the detector? 64 plus 32, that will be 96. Is it clear? This is a marking scheme. Uranium and the sources. And then suggest one reason why the count rate measured 1200 minute may differ because these radiations are random, fluctuation is there in the radiation. That's why it will continuously change. Like you predicted that you should get 96 radiation, but maybe after 1200 minutes you are getting 97 radiation or 100 radiation, because the radiations, it's a random process, there's a fluctuation. That's why you know may not have an exact number. So this is the last part for today's class in which we discuss atomic physics question.